Good afternoon. So for today and tomorrow, I'm going to give 3 lectures about a subject that's very dear to me, mainly biophotonics with diffusing light. And I have a bunch of different goals, but my goals for the lectures are, first of all, to sort of give you the underlying sort of physical structure of the diffusing light theory. And then the other one is to the other 2 lectures actually are oriented towards applications for cancer and for brain. And so for today's lecture, though, it's sort of a little bit too bad that it's the last lecture of the day because it's going to be more mathematically oriented. And so just feel free to interrupt me and ask questions. What I've tried to do is to the purpose of this talk is really sort of to direct you about things that you can then learn about, teach yourself. And for example, this review is a good place that fills in a lot of the details that I'll talk about that you can look up. But basically, I want to be rigorous as I can at the outset, and we'll take it from there. Okay, so here's my plan. Okay, so I want to very briefly give an introduction, and then I want to talk about optics that you all know about very well in the simple systems that are optically thin or single scattering, so we're all on the same page. And then I'll sort of progress into the highly scattering samples, okay, like tissue. And what I want to do is to first introduce the linear transport equation for light transport in turbid media, and then show you how you get to the diffusion equation. And then, as I promised, this is mainly a mathematical talk, but basically, and then I'm going to, tomorrow I'll remind you about the important things, so you don't have to feel like you need to understand every detail here or remember everything. I'll remind you what's important. But it's good to see it, I think. We'll talk about solutions, and boundary conditions and things like that, and other simpler approaches like the modified Beer-Lambert approach to analyzing diffuse optical data from turbid media like tissue. Then I'll sort of finish off with getting closer to looking at physiology, namely I'll talk about absorption spectroscopy and fluorescence imaging, or fluorescence measurements in turbid media. Okay, so the goal then of diffuse optics at some level is to do an in vivo biopsy and to do it on chunks of tissue, big chunks of tissue, millimeters to centimeters in size, and these chunks of tissue could be millimeters to centimeters, many centimeters even below the tissue surface. So that's the goal. And and if you just held up a flashlight to your hand, you know that it's possible to get light to go through your tissues, even when it's thick. And especially, that's sort of clear if you look at the main absorbers in tissue, which I've shown here. This is the absorption coefficient versus wavelength for water and oxy and deoxyhemoglobin. And the main thing is that there's this window in the near infrared where their absorption is relatively low. So you can have light penetrate deeply into tissue, but on the other hand, it scatters a lot, okay? So in principle then, if your light's penetrating, at least you're going to have some sensitivity to physiology and some contrasts, I'll show you tomorrow, that are complementary to other diagnostics. And you can do these measurements in a non-invasive, portable, continuous way. And so this is possible, and there are certain hard things about it. And the main thing that makes it hard, as I've said, is scattering, okay? So here's these are basically 3 pictures looking down on a sample where I'm shining a laser through it. And in the first case, there's a little bit of dust particles in the water, so you can see the laser if you look out this direction, but it travels in a straight line. If you add a little bit of milk, it broadens. If you add a little bit more milk, it sort of becomes like your tissue, okay? So this is the thing that makes it hard. The light scatters, and it scatters a lot in tissue. So what do we do? Okay? Well, we can make progress, but we have to sort of abandon traditional optics and embrace diffusion. Okay, if you do that, then you'll have a mathematical model where you can that you can use to understand your data and to separate scattering effects from absorption effects. And so I'm going to, in general, talk about two kinds of things that we do, one imaging and one monitoring. It's certainly much easier to do the monitoring, but I'm going to give examples of imaging in the context of cancer and breast cancer imaging. And then I'm going to give you, this is all tomorrow, I'll give you the monitoring stuff really all in the context of brain. Okay? But of course you can do brain imaging at some level near the surface. And you can certainly do lots of things with cancer monitoring. For example, during PDT, we just heard some PDT stuff where there's some value there. Okay, so let me then just start, and I'll start with the light transport and the very simple systems, the optically thin systems that you know about. And sorry if this is too easy, but basically in the thin system, basically what we want to do in all of these problems is to shine some light in, and look at what gets through. Okay, that's the simplest measurement. And the way in which light is lost from the incident beam we need to understand, and if we can understand it, we can learn something about the medium through which it's traveling. Okay, or another thing, of course, is it can be changed. It can be changed in a lot of different ways. And if we can understand, in the simple system what's happening, then we can extend it to this turbid media. So the big workhorse for everybody is absorption. This is just linear absorption. This is an optically thin sample. So that means that basically there's relatively little absorption in this sample, okay? So just imagine that I have water, and I put a dye in the water. I shine some light intensity I0 on the sample, and I measure some transmitted intensity. It obeys this very simple, well-known law where it's exponentially attenuated. And this mu A is called the absorption coefficient, and it depends on the concentration of my absorbers in the medium and on their extinction coefficients, which also depend on wavelength. Okay, that's important. So this very simple measurement is very powerful because it can tell us what are the molecules that are present in tissue. It can tell us something about, if we do it right, what are the concentrations. And even in principle, it can be telling you something about their local environment through the way the spectra shifts or broadens. Okay, so that's the simplest and most important class of measurement, I think. The other one, though, that we have to think about, and it's important also, is scattering. Okay, so here, and just imagine now we have a sample, again, water. Don't put any fluorophores or dyes in it. Just put particles in it or macromolecules that can scatter the light, okay? And so here we can do the same experiment in that case, shine in light some I0, measure some transmitted intensity, and if we're in the limit where there's single scattering, okay, so that there's either no scattering event or one scattering event as the light traverses this medium, then again, this will depend exponentially on the sample length and also on this so-called scattering coefficient, which is related to the number of scatterers. Okay, so if it was particles, it would be the number density of particles. And the cross-section of those scatterers, which is, again, wavelength dependent, the total cross-section of those scatterers. Okay, so that's pretty similar, right, to what we had for absorption. Scattering is a little bit richer because we can put our detector off at some angle, right, theta, and you can get signal at these angles that are different from the transmitted angle. And basically, those signals that are scattered at different angles are related to the so-called differential scattering cross-section, or sometimes people call it the form factor. And basically, this total scattering cross-section, which I used in the last slide, is basically the integral of this thing over all angles. Okay, and so there's a little bit more information now about that you can get by looking at the angular dependence of the scattered signal. And for example, you can learn about the size of the particles, or you can learn about their index of refraction and their shape in principle as well. I want to draw your attention to one thing, because once we sort of have measured, if you like, or know something about this differential scattering cross-section, then we can compute other things, like this factor G is called the anisotropy factor. And basically, it's just sort of the average cosine of the angle of scattering. So it's a measure, if you like, of how far, people will use it. We're going to use it later because it's a measure of how forward the scattering is in any given event. And so, so far I've talked about this scattering coefficient, but later I'll talk about a photon random walk step or a reduced scattering coefficient, which is related to both this anisotropy and also this, scattering coefficient. Okay, so there's information about scatterers in this data. We can think about what are the scatterers in tissues. They could be, there's a wide range of them. They range from being organelles like mitochondria, nuclei, cells, but also you can have interfaces, filamentous networks that could act like particles. But in principle, there's information, if we can measure this well, about the concentrations of these things and about their local environment. For example, if the local fluid is changing its index of refraction, that would change the scattering signal. Okay, so if we combine them, so if I have now a sample in this optically thin sample still, where we have stuff that absorbs and stuff that scatters, and I do the same measurement, then I get an exponential attenuation that depends both on this absorption and the scattering coefficient. This is rigorous, this is well tested, okay? And so we'll come back to this. Because in the multiple scattering regime, you can think of it just as a sequence of these kinds of events that the light experiences as it travels through the sample. Okay, so I wanted to mention one other thing in the single scattering regime, which I'll be talking about a lot tomorrow in the multiple scattering regime, but not so much today. And that is that you can also, instead, if instead of looking at the intensity of the scattered light, you looked at the fluctuations in time of the intensity, or the fluctuations in time of the field, or for that matter, the fluctuations in space of the intensity, you'll see that they're not just some solid average value. They vary over time and have some average value. And there's information in these fluctuations that's captured typically by measuring what's called the autocorrelation function. So here, what I'm showing you is the autocorrelation function of the electric field. You could also have one for the intensity. And basically, by looking at these kinds of autocorrelation functions in time or in space, I'll focus on time here, you can do what's called, in the single scattering regime, still a dynamic light, so-called dynamic light scattering experiment. So let me tell you a little bit more about that. So this is a dynamic light scattering experiment in the regime where we have single scattering, okay? So again, the light's either transmitted or it's scattered, but only once. And so here, you can imagine we have a sample. It's got lots of particles in it. They're moving around. They're doing Brownian motion, for example. And I shine a light on them. And in the presence of this light field, right, each of these particles develops a dipole moment. So a dipole moment, right, is going to radiate if it's oscillating, and it'll radiate a field in all directions. So I can put my detector out here at some angle theta, and I can measure what's sort of the scattered light from these particles. And because the particles are moving, this scattered intensity will fluctuate in time. So sometimes they'll add up constructively, sometimes they'll add up destructively, and varying as they move, they vary in between destructive and constructive. And so again, this is the basic experiment. The information is derived by computing the autocorrelation function in time of this intensity, for example. So I take this intensity fluctuation, I translate it in time, and I multiply it by what it used to be. And then I get a number. So that's a number on this curve, okay? And from the slope of this autocorrelation function, I can extract motion about the mean square displacement of the particles. So in this case, it's a Brownian motion, so I can extract information about the Brownian diffusion constant for the particles, okay? And so that's very useful, for example, for figuring out the size of particles, among other things. And so basically, this is the other kind of measurement that I'll be showing you, and the reason that it's so powerful is because it lets me look at flow, blood flow, okay? Because basically, the blood flow in your tissues, it depends on sort of how much stuff is moving and how fast is it moving. And so I can measure blood flow responses by measuring these temporal fluctuations and looking at their changes, okay? So that's the last example of what I would say is the simple, well-understood regime. So now I want to turn my attention and sort of talk about the turbid samples, or like tissue, okay? And the first thing I want to do is sort of end up essentially at the diffusion equation for the photon fluence rate, it's called, okay? And but we'll have to take a sort of a few steps before that to get to that stage. Okay, so you know, tissues multiply scatter light, and I've kind of alluded to this earlier. We understand single scattering, and to the degree that we can imagine the multiple scattering problem, and you know, this doesn't always work perfectly in those kinds of photonic materials that you saw earlier. In fact, a lot of this could break down, especially when there's photon localization. But in tissues, it's actually a pretty good approximation. And that is, if I shoot light into a sample like this that's got lots of scattering, you can think of the trajectory, if you like, of the light as experiencing some kind of single scattering event, then traveling some distance, experiencing another single scattering event, and so on, as it sort of tortuously finds its way to the exit, okay? And so you want to be thinking about the transport in the turbid media like this. Now, you can ask the question of, is it a random, are these events independent or not? And that's a perfectly good question. Okay, so how can we start making progress on this? So the first thing is, you know, all of these theories, they better sort of be able to be started from Maxwell's equations, okay, for electric and magnetic fields. And so I'm not going to be deriving that, but for example, even geometric optics, right, with ray optics, that's a theory that can be derived rigorously from electromagnetic wave theory. The same is true for transport theory, but like I said, I won't. It's non-trivial to do the derivation, but you can see that it's sort of already using a lot more ingredients than, say, ray optics in its picture. So the key sort of character in the transport theory is something called the radiance. The radiance is the power per area traveling in a particular direction, okay? So it depends, and it can depend on position, it can depend on time, but also the direction matters, okay? And so it's related, you can think about if you think about plane waves in Maxwell's, in just regular light, then you know there's a pointing vector associated with plane waves that has some intensity associated with it that depends on the square of the field and some direction associated with it. So you can think of this fluence rate as sort of being related to this, okay? But you're going to have to average over polarization directions and things like that. So what the transport theory does, the linear transport theory, is it just balances the radiance in the volume elements in the sample, okay? So again, you can imagine that big turbid media, you can divide it into a bunch of small volume elements, and now you just have to think about what's happening to the radiance in those small volume elements. And so, if you like, the left-hand side of that equation is essentially the difference between the final and the initial radiance, and that's going to depend on the time derivative of the radiance in that volume element times some infinitesimal time, okay? Now, the time derivative, though, you have to be a little bit more careful with, right? Because it's a flowing thing, right, the radiance. And so you have to use a convective derivative, not just a direct derivative. And so that's going to involve the gradient of the radiance as well as the time dependence of the radiance. Okay, so that's sort of the left-hand side of the equation. And the right-hand side of the equation sort of looks at what can happen to the light, what happens to sort of the radiance in the volume. And so one thing that you can have is loss, okay? We've already talked about this. You can have loss due to absorption and to scattering, okay? So absorption, you just lose the photons. Scattering, it's just moved into a different direction, but it's no longer in the same direction. But the other thing is you can have gain, if you like. You can have sources, right? I can put a source of light, like a fiber optic, that is generating radiance in different directions. And also, I can even have a scattering, and this brings me back to that differential scattering cross-section that I showed you earlier. You can even have scattering of radiance going in one direction into the direction you care about. So there's different ways that you can grow the radiance and there's lots of ways that you can lose the radiance. Anyway, when you combine these, you get the transport equation. So I've written it in all its glory here, okay? And basically you can tell, right, this isn't going to be that easy to solve. Okay, it involves derivatives, it involves integrals, lots of things, but just to review it, there's a source term, right? This is like something like a fiber optic that I might put into my medium. There's a scattering term involving the differential scattering cross sections of your scatterers in your sample. There's loss terms, and so on. And the gradient matters too. Okay, so this is what we want to solve. And in anticipation of solving that, I want to introduce two new variables, which are related to the radiance, which are going to come out of our solution. One is called the fluence rate, that's phi, and basically that's sort of the angle integral of the radiance, okay? So that's sort of, if you like, the photon concentration, almost, right? You can think of it that way. And then there's the flux, okay, the photon flux, and that's also an integral of this radiance, but it's weighted by the angle that it's going, okay? So this has a directionality to it, all right? But both of these variables have integrated out, if you like, the directionality, and basically only depend on position and time. So to solve the diffusion, to solve the transport equation, again, I'm not going to solve it for you. I just want to give you sort of the postmarks. And that way, hopefully, you can see also if you're in a regime when you're doing an experiment, and we'll talk about this, where it's, diffusion may not work that well, you'll see what you have to do. But anyway, the way you solve this is you essentially expand all your variables in spherical harmonics. So this is something you know about if you're doing a lot of electromagnetic problems in physics. And essentially, you stuff all this back into the transport equation and then just collect the terms at different orders, okay? So if I collect the lowest order terms, 0 and 1, effectively what I'm doing is I'm assuming that the radiance is mostly isotropic, okay? Because the 0th order is the isotropic contribution, the 1st order is the lowest order anisotropic contribution. Anyway, you take this, you stuff it into the theory, and you find that the radiance depends on two things, like I've told you, the fluence rate and this current, this flux. And so I can compute it if I know the fluence rate and the flux, okay? So now I take this, stuff it into the linear transport equation, manipulate it, approximate it, and now we get to where I really want to get, is you get the diffusion equation, okay? So the diffusion equation is an equation of motion, if you like, for the photon fluence rate. That's that phi, that isotropic contribution of the radiance. There also, you get some relationships as well between that relate the fluence rate to the flux. So let me write this down. Here it is again. This is the diffusion equation for the fluence rate. So phi is this fluence rate, or photon concentration. You have your source term. Here's the change in time. You can have absorption. And this is diffusion. D here is the diffusion constant for light. It depends on the velocity of light. It depends on this scattering factor, mu s prime, which is related, remember, to this scattering times 1 minus g, the anisotropy. And this is basically the random walk step. So mu s has dropped out of my theory. G has dropped out of my theory. They come in together as this random walk step. The other thing that you learn is that the flux is related to the gradient of the fluence rate. Okay, so this, if you know about diffusion, this shouldn't be very surprising. If you don't, you have to sort of think about it and how to use it. So let's just stop for a second and think about what have we gained. What we've gained is we have really a diffusion equation is a lot easier to solve. People have been solving it for 100 years. And basically, we have a tractable mathematical model for the transport of the photon concentration of the fluence rate through a turbid medium. That's gaining something. And furthermore, we have a connection, an explicit connection between the fluence rate and its transport and the optical properties of the medium, like the scattering coefficient, like the absorption coefficient, stuff that we know have a meaning to, okay? So let's just take a step back and think about what are some of the assumptions that I've made, okay? So to use the photon diffusion equation, I've assumed essentially that this scattering length is small compared to the absorption length, okay? So there's many, many scattering events before there's an absorption event, okay? I've also assumed implicitly by doing the P1 approximation that the fluence rate is much bigger than the flux, or the radiance is mostly isotropic. Okay, so then I've sort of assumed a few other things that I've swept a little bit under the rug. I've assumed that my sources are isotropic, and I've assumed that the scattering in the tissue, it doesn't depend on the angle. It just depends on the difference in the angles, okay? That's a statement about the form factor. And then finally, I've assumed something about the modulation period, okay, or the sort of the time variation, if you like, of the radiance compared to the time between the random walk steps, okay? So these are things that you might think could be wrong, or might think could be questionable, but it turns out that in tissue, most of these assumptions are pretty good. You certainly have this situation where the random walk step is much, much shorter than the absorption length. Okay? In a typical tissue, the random walk step might be about 1 millimeter. The absorption might be on 5 to 10 centimeters, depending on the tissue. Certainly, tissue is not perfectly anisotropic all the time, but it's fairly anisotropic on a millimeter kind of length scales. And then, as long as we're far from the source, these approximations about sudden variations of the signal are probably good, and the time variations, as long as are relatively slow. And so it's all of these approximations that we've made are basically okay for looking at deep tissues, especially in light of one important thing I want you to remember, is that these aren't really precision measurements. Okay, it's not like I'm trying to measure the energy level super precisely in a hydrogen atom or something. These are measurements where we just want to figure out roughly the concentrations and how they are changing of oxy and deoxyhemoglobin, for example. Okay? So basically now, what I've gotten to is, I hope you can see that I've been taking a somewhat rigorous approach, and I've gotten to the diffusion equation. And now you can sort of go back to this picture of scattering events, a series of scattering events. And essentially, the only thing that we're really assuming in the end is that we have a bunch of single scattering events, and they're sort of independent. Okay, they're random with respect to each other. So the next step then is to look for solutions of this, because in the end, I'm going to make a measurement, right? I'm going to put light in over here in my tissue and collect it over here, and I want to relate the measurements to the properties of the tissue, okay? So to do that, you're almost always going to be fitting a function, fitting your measurements to a function. So we need to look at the solutions. So I want to talk about some analytic solutions. And so first, we'll just talk about the absolutely simplest case, which is if I have a homogeneous medium, and it's turbid though, okay, so it's multiply scattering, and it's infinite, okay? So I want to look at the solutions of that, because that's going to give me some intuition. So imagine that I have a tank of milk, or intralipid in this case, and I take a light source, a laser, and I put it into the middle of that. I'm going to make a point source, and I'm going to ask what should this look like in the medium, okay? And so we can understand that by solving this diffusion equation. So I'm going to talk about, most of the things I'll talk about are in the frequency domain. So let's just imagine that my source, that's what S is a point source. It doesn't have to be a point source, but let's start that way. And it's just oscillating in frequency at some 100 megahertz, okay? So the amplitude of this source is turning on and off 100 million times a second, all right? And then I can look for solutions for my fluence rate that are also oscillating at the same frequency. So I'm going to put in a source. It's this red curve you can think of, and I'm going to measure some fluence rate of different positions, which will be maybe this represented here by this blue curve. So the amplitude will be decreased, and there'll be a phase shift. The crests will be displaced with respect to each other, okay? And so essentially, did it get dimmer? Looks like my... All right, well, we'll live with this. So anyway, let's go back, sorry, one step. So if I take this diffusion equation, I stuff these in here, I can rewrite it like a kind of an equation that will give me a wave, but it's an overdamped wave, okay? If you like, the wave vector depends on both the absorption, the diffusion constant for light, and this frequency. And so let's look at that a little bit more carefully. It's basically the point source, or the Green's function solution to the diffusion equation in the frequency domain. So I'm going to get a wave that looks like e to the I k r over r, a point source, a spherical wave. It has but the k has real and imaginary parts. One of them, right, the real part is going to define the decrease in the magnitude with position, and the imaginary part is going to give me the oscillation in the phase. And so these things, these real and imaginary parts of this wave vector, are related to stuff that I care about. It's related to the frequency of the modulation. It's related to the absorption coefficient. It's related to the scattering coefficient, okay? And that's the tissue properties. And so I can do lots of measurements that you can imagine. For example, I could change the frequency. There are lots of different ways to extract this information about the sample from this kind of measurement. So let me just show you, here's the measurement we did many years ago, really, in this tank. And so here is a plane in the tank. My source is right here. These curves, so this is position. And these are the constant phase contours. So it's nice and spherical, emanating from the point source. And if I plot the phase versus source detector separation, or the amplitude, or the log of the amplitude versus source detector separation, I'll get two straight lines. And from the slopes of those lines, I can get those real and imaginary part of the wave vector, and I can figure out what's the absorption and the scattering in my sample. Okay? You can do more. You can have a heterogeneous medium, okay? So here we have a heterogeneous medium, and going from whole milk, skim milk into whole milk, or whole milk into skim milk in this case. So you can see these are measurements, right, of the wave fronts, and they change. You can have objects. This could be like a tumor. Again, these are all measurements, and you can see that the wave fronts are distorted by this object. And again, the source is here. It's a point source. And so from the distortions of these wave fronts, you can imagine that you could work backwards and figure out the properties of this object. Again, like a tumor. Okay, so that's the name of the game for the solutions in the infinite medium in the frequency domain. So then, I just want to mention that I like the frequency domain, but you can also work in the time domain, okay? And basically, they're Fourier transforms of each other. And so in that experiment, what you do is you put in a short pulse over here, say, and over here you measure the pulse, the time distribution of the arrival times of the photons. And basically, the shape of this curve looks like this, okay? And so from the shape of this curve, I can extract, again, the absorption coefficient and this scattering coefficient of the tissue. So there are two sort of complementary ways to make a measurement of the optical properties of this turbid medium. Okay, so what have we gained? Well, we've gained, number one, that we can separate the absorption from the scattering, okay? That's a big gain, okay? We've also, once you do that, of course, then you can measure the absorption, or you can measure the scattering. So you can learn something about the tissue, the concentration of the absorbers, the nature of the absorbers. Same for the scatterers. And so, in the end, what I want to do is to take a set of measurements, right, and fit them to a theoretical prediction, okay, to get the absorption and the scattering. And so in this case, in the infinite medium, in my frequency domain measurements, I'll just measure the amplitude and the phase of these diffusive waves at different positions. Or I could also measure it versus modulation frequency. In the time domain, I'll just measure the photon arrival times. Again, it's better if you do it at a bunch of different positions to build in some redundancy. But that's what you want to do, and it's very nice that the solutions are analytic. All right? So in the infinite homogeneous turbid media, we're in good shape. But what about if the medium is heterogeneous, okay? And of course, we don't live in a homogeneous infinite universe, and neither the tissue is never that way. And certainly one problem that we want to look at is like the brain, okay? And that's anything but infinite, semi-infinite, and homogeneous. So we need to now, to make more progress and to make it more quantitative, we need to sort of think about how can we handle heterogeneous media, okay? And so the simplest heterogeneous media you can imagine is what arises when we have a semi-infinite turbid medium, okay? So for example, you can go from air to tissue, okay? And so generally, again, I'll have some source fiber. So this is air, this is tissue. And I have a source fiber and I have a detector fiber on the surface of that. And I need to figure out what will I measure, okay? And I've so far only figured out what I'll measure in an infinite medium, okay? So the trick is that we need to figure out what's the boundary condition for the fluence and the fluence rate and the flux at these interfaces, okay? And so again, I'm not going to go through the details too much, but I just want to make one physical comment. The key to solving this is to realize that the radiance that's reflected back into the medium is basically proportional to the radiance that's going to the surface, okay? So this radiance is reflected back into the medium, and that depends on what's going to that surface, and then the proportionality constant is some number that depends on the Fresnel coefficients that you know about from electromagnetic wave theory for P and S polarized reflection. You have to average over those, okay? So this is the key realization. And then, so for example, right, if I wanted to figure out the current, the flux going back into the medium in the plus z direction, I can figure it out using the fluence that's in this medium, the radiance that's in this medium, and this relationship, okay? I can solve that. And what you find when you do that exercise is that you get a well-defined boundary condition. It's called a partial flux boundary condition that relates the fluence at this position of the boundary to the gradient of the fluence at the boundary, okay? And the proportionality constant is a length that depends on the scattering factor that's in the D, and it depends on this Fresnel coefficient, okay? So this partial flux boundary condition, to the extent that we can think about this problem as exact, is exact, okay? And so this diffusion equation plus a boundary condition can give you any solution, right? You can solve it analytically, if you're lucky, or you can solve it numerically. I'm going to show you now one further approximation of this partial flux boundary condition that lets you really solve it very easily using the method of images, okay? So again, just to go back to the original problem, typically we would have a source fiber on the surface and a detector fiber, maybe many detector fibers. And so for the source, right, it's shooting photons in, but after they traveled one random walk step, they're kind of randomized. So typically what people do is they replace the source by a point source, an isotropic point source, one random walk step in, okay? And then this radiates in all directions. And then if I Taylor expand this fluence rate near the surface, you can find that actually you can make a prediction that the fluence rate will be 0 in this plane here. Okay, so not on the actual surface, but at a surface behind it. Okay, and this plane is related to this extrapolation length that I showed you earlier. And so once you know that it has to be 0 here, you can use the method of images to solve any problem like in the plane. Okay, this is what we know again from electricity and magnetism. And so, for example, if I solve it, I can basically know that my solution in the medium is the sum of this +1 source and then an image source that's negative that's exactly reflected around this 0 plane. And so it's a sum of two terms, two spherical waves. You can make some approximations about it, and you get a pretty simple solution for how your signal should change as a function of separation on the surface. And I just draw your attention, it's exponential, but it depends on 1 over the separation squared. In the infinite media, it depended on 1 over the separation. And so here's a measurement. You know, this is sort of the workhorse approach of the field at some level. Essentially, I hope you can still hear. I think, oh, yeah. No, it's okay. Can you hear? Okay. So basically, this is a measurement that we did on the head. So we have a bunch of source detectors. So I'm plotting the magnitude of the amplitude versus the source detector separation, the magnitude of the phase versus the source detector separation. I get two straight lines like I expect from this function here. And from the slopes of these lines, I can extract the optical properties. So again, that's really powerful. Now in a more realistic medium, I can figure out what the average optical properties are. So, you can have other media. So for example, you can have the slab. The slab is just an infinite series of images, right? So, and they get smaller and smaller, their contribution as they get farther and farther away. So this is a nice, easy way to solve that. You can do it on a computer. I've so far talked about the interface between air and a turbid medium. But you could also have an interface between two turbid media, like a tumor and the surrounding tissue. And so you can solve the problem for a spherical heterogeneity exactly in a semi-infinite or an infinite medium, but you have to apply boundary conditions that the normal component of the flux is continuous across the boundary, and the fluence rate is continuous across the boundary. And then you can solve this exactly. It's a painful thing, but again, if you've taken any electricity and magnetism course, they solve these problems. And you can get, for example, these are the changes in the amplitude versus position, constant phase contours. Here's changes in the phase versus position for this object and a source over here, okay? So again, let's think about what we've gained. Basically, what we've gained now is we can separate and measure the tissue scattering and the tissue absorption in a piecewise homogeneous turbid medium, okay? We started with basically a lot of uncertainty. Now we're sort of reducing that. And so if I want to measure, I can measure the absolute absorption and scattering coefficients of my media, but I need to have data, either phase and amplitude data in the frequency domain or time response data in the time domain. Ideally, I want to have many sources and detectors if I can. And then I need a model, and I've given you the model. These are analytic models. You don't even have to be analytic. We can do it on a computer. So then basically all you do is you're fitting your data to your model and finding the best absorption and scattering to describe the data. Okay, so I want to talk about one other technique, which in this same context, and basically, it's called the modified Beer-Lambert law. And basically, the reason is because it's widely used in the brain community, especially, to look for changes. It's much easier. You can do it with CW lasers. You don't need modulated lasers or pulsed lasers sources. And it's useful, especially when you have a baseline condition and you're measuring a perturbation. And what it does is it lets you go from the measurements of changes of diffuse light fluence rate, changes in absorption directly. So let me sort of show you how that goes, okay? So again, just to say it again, the so-called modified Beer-Lambert law sort of is a term that people use to describe this kind of analysis. And again, I just want to mention it's mainly useful in studies where you have a baseline situation and you're comparing the baseline to some functional activation or some, injured region compared to non-injured region. There always has to be a comparison, okay? So again, just to remind you about the Beer's law, the Beer-Lambert law, which we talked about already in the thin medium. I have some light that shines in. I measure the light that's transmitted. If this medium is changing, it might be changing in time. And this intensity that I measure will depend on my input and exponentially on this absorption. And so often what people use is they describe this, they take the log of this ratio and they call that the optical density. So the optical density is something that I measure and it's related to this absorption times the length, all right? So what the modified Beer-Lambert law does is it basically says, well, I have an OD, it expands the OD around some baseline value. So I have some optical density that I'm measuring in my tissue. It's close to my baseline value, but I'm allowing, if the tissue is changing its optical properties, like its absorption, which is represented here by delta mu A, or scattering, which is delta mu S prime, then I can just, if the changes are relatively small, I can do a Taylor expansion. And these things are, this number here is known. I mean, you can determine it or estimate it from theory. Same with this number. And this number is that you measure. So the OD, right, before we had it was the log of the intensity. The delta OD, the change in the OD, is comparing my measurement of intensity at some perturbed time, functional activated time, to the baseline time. So the log of that, you can show, is related approximately to the change in the absorption in the tissue times some length. And this length is the mean path length traveled by the photons in going from the source to the detector. But again, it's something that is basically this derivative, okay? Which is, you can determine from the analytical solutions that we have. So what we can do, what's really great, is that measurements of an intensity change, so you can even apply this to CW lasers, basically are proportional to changes in absorption. So it's a very, very easy way to measure changes in absorption, okay? Without knowledge of the absolute value, I mean, or with an estimate of the absolute value. So it has weaknesses too, but it's much, much simpler to implement this measurement, and it's fairly robust. And so, for a brain problem, right, tissue applications, you can think of the medium as semi-infinite, which is what I did when I showed you the data earlier, but you can also sort of realize, well, they're layers, okay? And at least you could say that there's two layers, an extracerebral layer and a cortical layer, or a cerebral layer. And so I'm going to shine light, and it's going to go through both of them. And I want to look at the changes. Can I apply this same idea in that case? And the answer is that you can. But let me first say that you could also go back to diffusion theory. And again, don't worry about the details. But you can solve this problem exactly for two layers for what you should measure that depends on the properties of this. And so in principle, if you had many source detector separations, you could fit to this and figure out the absolute properties. But if you only care about the change, then you could show that the change in the OD, again, that's the change of the intensity that you measure compared to the baseline value, that just depends on now some length, average length of travel through the overlayer tissue times the change in the absorption in the overlayer tissue times the extracerebral and the cerebral tissue. So, you know, this is one measurement and kind of like two unknowns. So you can see that, the next thing you want to do is to have at least two, one long source detector separation, one short source detector separation, and then you can extract the changes in absorption in both the extracerebral and the cerebral tissues from measurements in changes in intensity, okay? So that's sort of what I was just saying here, okay? So, so basically what I've done is I've so far gone through the case of using diffuse optics to monitor tissues, okay? But you can do a lot more, okay? The next level of it is to do tomography, okay? So I just want to give you a flavor for how that works, okay? So in tomography, which is sort of real imaging, you have to solve an inverse problem, okay? So you make measurements on the surface, and you try from those measurements on the surface to go back and make measurements in the medium, okay? So just to understand this, I want to go back to that problem of the spherical heterogeneity. And so you can imagine that I have some incident diffusive wave traveling through the turbid medium. There's some heterogeneous tissue in the turbid medium that's going to scatter this wave. And so I can measure the phi scattered. So in general, when I measure out here is some sum of the scattered wave and the incident wave, okay? So now, so that's the basic thing. And essentially what we want to do is to relate the scattered wave measured all over this boundary to all the different heterogeneous volumes inside, okay? So what you can do, to be more quantitative about that, is I can write the absorption as some average value plus some changing value. I can write the diffusion coefficient for light as some average value plus some changing value with position. I can put them back into that differential equation for the diffusion. And then I can look for solutions which are essentially the sum of the unperturbed plus the scattered wave. I can do that in different ways, with a Born approximation and a Rythoff approximation. So for concreteness, if I just let the scattering fluctuations be small and focus on the absorption coefficients, we know we can figure out the scattered wave. It's basically a solution, which I'm going to just show here, which depends on essentially the propagation of the source to every point in the medium, and then there's a strength in the delta mu of that point in the medium, and then there's a re-radiated wave from that point to my detector. That's what the Green's function is here. So I have phi naught, that's my incident wave, going from my source position to every point in the medium. There's sort of a strength of absorption heterogeneity at that point R, and then that causes a scattered wave which propagates from R to the detector. And then I have to integrate over all points in the sample. So this is a complicated relationship, but you can write it down as a matrix equation, where I have a vector of measurements and a vector of absorption properties at different positions in the medium, and then a matrix that connects the two, and the matrix depends on that Green's function and the incident wave. Okay? And so essentially you have something that looks like this, a set of linear equations, and you can invert this. Now, that's saying a lot, but you can invert it and then multiply that inverted matrix times your measurements to get your absorption. So that's basically the simplest version of doing tomography with diffusive waves. And it's a reasonably well-posed problem. It's not perfectly well-posed, okay? So this approach is conceptually correct, but it's a nonlinear problem, and so you want to generally do this iteratively, okay? So there's generally what you do is you sort of assume some initial properties of your medium, then set up a forward problem to calculate what's the fluence rate at the boundary, then compare that to your measurements, and then from that comparison, you calculate a chi-squared. If the chi-squared is not very small, then using that data, the difference between the measured signal at particular source and detector and predicted signal for that source and detector, you can update your optical properties. And then you just do this iteratively again and again until you get sort of until you get satisfied that you have a small enough error. So this is sort of an iterative approach. This is the most standard way that people do these problems. I will point out that the problem has, as in many inverse problems of this nature, is ill-posed. So you typically have to do something called regularization, which is where you put in a penalty for too fast a fluctuation, or a penalty for too big a deviation, okay? So again, that's something that putting in constraints, which you can do because we know something about the physical problem. But I just want to emphasize that I've just described a very big subfield of the community in one slide, okay? And so there's lots of people working on this problem, and have been working for a long time in many cases, and with many different approaches to imaging, and there's all sorts of things to know about this that I've completely not discussed, and there are trade-offs that you can make, especially with regularization. And so but two of the most famous ones, if you're interested in this, there's a software called Toast and a software called Nearfast from Simon Arridge and Hamid Dagani. And basically, these are actually available softwares that you can download and use. You have to understand them a little bit to use them. But, and then, you can build your own based on that. So this is sort of the iterative approach, I would say. And then there are analytical approaches, actually, where people use spatially modulated light in special geometries like slabs, but that's like, again, a good geometry for a breast compression. And then you can actually very quickly, in one step, make a very good initial guess, okay? And so that's useful if we want to get real-time information in the clinic. These iterative approaches generally, of course, there's more and more computers getting faster and more parallel, so it always is going down in time. But these generally, iterative approaches take longer, okay? So that's what I wanted to say by way of tomography. And then I just want to finish up with trying to start to connect it back to the physiology. And there are two things I want to discuss, mainly absorption, but I want to allude to a fluorescence because I'll show something about that. And so the lectures tomorrow, if you hated this mathematical lecture, They'll be different, okay? Okay, so don't be discouraged. I will remind you what you need to know, but let me just start leading up to that. So the biggest thing is I've only told you about measuring optical properties. I've told you about measuring delta mu s prime, delta mu a or mu s prime, or the changes of them. But really, we care about what's the change in the physiological property. And the where that we can get that is we can get that from spectroscopy, okay? We can get that because we can make measurements. In all optical kinds of experiments, you make measurements at many different wavelengths. So again, going back to that initial plot, sort of zooming in the near infrared, the oxyhemoglobin and the deoxyhemoglobin in the water, and the lipid for that matter, they all have different spectra in this region. This is the extinction coefficient, if you like. And so if I make measurements at more than one wavelength, then I can, and I separate scattering from absorption at each wavelength. I basically measure absorption at each wavelength. And that's going to be related, if we just forget about the water, say it'll be related to the concentration of deoxyhemoglobin and oxyhemoglobin times the extinction coefficient of each of these, right? And so this is two equations and two unknowns, and I can figure out then the concentrations of oxy and deoxyhemoglobin in my tissue. This is the most important thing that people determine with these diffuse optical techniques. So you can determine the total hemoglobin concentration in your tissue. You can determine the total oxygen saturation, so the amount of hemoglobin that's oxygenated, or STO2, from the wavelength of this phase and amplitude, or from the wavelength dependence of the time broadening signal, okay? And so let me now just say a little bit more about why you care about that, because everybody really does care about that a lot. Okay, so you want to think a little bit about the vasculature. So just to remind you, the circulatory system, right, it has the arterial side, the venial side, and the capillaries are connecting them. And the oxygen is brought in the arterial side, and then it's used by the tissue. It's transferred from the venials and arterioles and capillaries to the tissue by diffusion. And it diffuses, basically, the oxygen gets loaded up on hemoglobin in your lungs, and then it goes through in your blood and in your red blood cells, and then it offloads because it's in equilibrium with the partial pressure oxygen in your tissue. And so, here's sort of a, just don't worry about this, but this is the plot of hemoglobin saturation. Remember, 100% is arterial side, and then this is PO2 in your tissue. And it's a sort of an S curve here, or a sort of a saturating curve. And so you can see that if I make a measurement of oxygen saturation, it's also effectively a measurement of tissue PO2. And so why is that useful? And I can do that again as on an average, the average value of a tissue in a monitoring experiment, or I can do that in imaging in different volume elements in the sample. Okay? So why is that useful? Because we can detect a situation called hypoxia or hyperoxia, okay? So you can think about, like, your oxygen comes in through your arterioles, the tissue does work, and then the leftover goes out through your venials. If the arterial oxygen is too low, you're on a mountain or something, well, you'll have a deficiency of oxygen. If your blood flow is too slow, you can have ischemia or clotting, then you might also have hypoxia. If your metabolism is too big, you can get a hypoxia. There are lots of different ways you can get it, but often that's a situation that's not that good, and clinicians want to know about it. And so by doing the spectroscopy with diffuse optics, I can look at deep tissues, big chunks of them, millimeters to centimeters, centimeters below the tissue surface. I can look at that, and I can diagnose something about the tissue function. And so in a case of a tumor, the vasculature of a tumor is really quite different than the vasculature of the normal tissues. And so that's a great candidate for there to be optical contrast, all right? And also, of course, the saturation. The oxygen, you can have hypoxic tumors that has consequences. So there's other things that can be different. And so just again, I'm not going to show, I'm just showing you, I'll tell you a lot more about this tomorrow, but here's like a measurement of this is a slice out of a three-dimensional image of a tumor by Regina Cho, of a tumor, and here I'm looking at its hemoglobin concentration compared to the background. Here I'm looking at its oxygen saturation compared to the background. Here I'm looking at the scattering compared to the background. Here I've constructed an index out of all of these that's optimal compared to the background. Basically, you have a new kind of contrast that you can image about a tumor. to tell that it's different than normal tissue. And this can be very useful, and I'll show you some ways that it might be useful tomorrow. So that's connecting absorption to physiology. And then one more thing I wanted to mention that I hadn't said anything about, and that is endogenous versus exogenous contrast, okay? So everything I've been talking about so far as physiology is relying on the fact that blood, is relying on the fact that blood, well, it's mainly relying on vascular effects, but it's also it's entirely relying on the fact that your tissue physiological properties have to be different in a disease state compared to a normal state. But you also, there's a lot of work nowadays, and Gang Zhang is going to talk about this next week, with fluorophores, nanoparticles, all sorts of interesting, innovative kinds of tracers that can be used to enhance tumor contrast, for example, or to measure flow and things like that by their uptake. And we want to be able to try to take advantage of that. Often these things are fluorescent. And so the last thing I wanted just to mention is that we can, with all of this apparatus that I've showed you, this mathematical apparatus about diffuse optics, you can use it to look at fluorescence in diffusive media too. And so let me just say a tiny bit about that. Okay, so here's a molecule called indocyanine green. It's one of the few molecules that's actually it's FDA approved in the United States. Basically, it has an absorption that's this black line here versus wavelength, and the emission is redshifted, right? It's over here. So you can think about conceptually, we'll shine a diffusive wave in at an excitation wavelength, and then the atom and the molecules in their excited state, they can either non-radiatively decay, or they can decay and give emission. Okay, let's just forget about the non-radiative decay. For the moment, that just ends up degrading the quantum efficiency of the process. You can actually write down an equation for the rate of change of the number of excited molecules versus time in terms of this decay rate and in terms of the absorption extinction coefficient for the drug and the amount of light from your incident wave at the drug at a position R and the number of molecules at that position R. Then you can solve this, and you can see there's a very simple result that I wanted to show you, and that is that the number of photons emitted, fluorescent photons at a particular position R, is related to essentially the concentration of the molecules at that position, the photon fluence rate at that position, the excitation fluence rate, and then also this relaxation time, okay, this lifetime of the state. And so you can go back and you can think about this problem that I posed for you for the inverse problem for diffuse optics. The fluorescent signal in an infinite medium, it's going to depend on my excitation going from some position R1 to a position here. It should have been R here. R source to R1 in the medium. Then there's this transfer function that I just showed you that depends on the concentration of the fluorophores and the lifetime. And then there's essentially a Green's function that describes the fluorescent diffusive wave. And you can put these numbers in, you can do the integrals, and you can get a very simple analytical results again, okay? I won't dwell on it, except to say that you can get them. They're a little bit more complicated than they were for the straight absorption problem, but they're not that much more complicated, and there's more information. You can look at the drug concentration, and you can look at the lifetime of the drug, which can be related to the local environment. And finally, you can imagine that, suppose that you just had a tumor where there was a much stronger uptake of an exogenous contrast agent compared to the surroundings. Well, you can have an excitation wave going in and then a re-radiated diffusive fluorescent wave coming out. So this is the basis of an imaging approach, tomographic imaging approach that you could have to use contrast agents in turbid media to do tomography. So again, this was a whirlwind, and probably I hope it was okay for at least some fraction of you. But basically, I wanted to just spend some time and really get to the foundation of the field And then tomorrow we'll have one talk about the cancer imaging and one talk about the brain imaging and the issues of that. And so then I'll bring up the results that you need to understand. There'll be one sort of technical thing about flow that I want to talk about, but basically you have all that you need. Take a look at that paper if you're interested, or come and ask me, talk to me. Okay, thank you.
Thank you, Professor Yodh. Any questions for Professor Yodh?
Thank you, Professor. That was very informative. My name is Akash, and I mainly have some clarification questions.
Yeah.
So first is, while writing the forward model, designing the heterogeneous medium like tumor in the tissue, I saw that you ignored the change in scattering coefficient, and you modeled only the change in the absorption coefficient. So I was wondering what's the reason for that?
The only reason was conceptually making it easier to understand. Okay.
Right.
In fact, in practice, we do both. Okay, but it's not as nice, it's not as pretty.
Right.
It's not as clean. But in the practice, in the end, most of the time, I'm doing iterative approach. You can do also those angular spectrum approach with this modulated waves, but that one, you can do it with the variation in D as well.
And also for the iterative approach, I think we have to solve for the boundary conditions, right? But solving for boundary condition also involves that I know about the location of the tumor from
No.
beforehand. No?
No, you just need to know, so again, in the case of you need to know where your boundary is, and you need to apply the partial flux boundary condition. In that case, once you go to doing it numerically, then you might as well not do the method of images, okay, for tomography. So then just do the partial flux boundary condition.
Okay.
And that's what you do. Yeah.
And I had another question about the dynamic light scattering, where you showed that whenever there's colloidal particles in the solution, there is some intensity fluctuation at the detector. And I was wondering...
there's an intensity fluctuation because they're moving.
Right.
With respect to each other.
Right.
Right.
So I was wondering how is that fluctuation related to the particle movement and all? For one thing, it's related to the velocity, but...
No, okay, so in that particular problem that I gave, the particles are doing Brownian motion. Right. So on the time scales that I'm looking at it, really the mean square displacement of the particle is 6d tau. Right. So literally, you're measuring the diffusion constant of the particles.
And I was thinking if the concentration of the particles is also related or not.
So the concentration is not related to, in this particular situation, in the single scattering case, it doesn't actually, I mean, you need to have sort of an ensemble of them.
Right.
But it doesn't matter for this problem what the concentration is, except the size of the signal. But it will matter for the case of the multiple scattering case.
I see. Okay. Thank you, Professor.
Yeah. Yeah.
So thank you for the great presentation. Covered a lot of ground. But I wanted to ask something in particular. One of your slides, it was looking at tumor contrast in breast tissue, and you sort of, I think there was one oxygen saturation or hemoglobin. I want to know if you knew what wavelength of light they were using and what wavelength seems to be most optimal for that sort of situation.
So, by the way, that was my group, that Regina, but basically, so we actually had like 6 wavelengths. So what we did is it's like I showed it with 2 wavelengths, but it's really better if you have more than 2.
Yeah.
Right. It's better to over specify your problem. So we have a spectra at 6 different wavelengths, and we find the best fit for that spectra to get the concentration. So the optimal wavelength, so ideally you want to have, so superficially, right, if you notice the oxy and deoxy spectra crossed.
Yep.
Right? So that's called the isospectic point. So in principle, if you measure there, you're just measuring the total hemoglobin concentration. And then if you measure on either side of it, you're sensitive to oxy on one side or deoxy on the other side. So you really want to span that region, okay?
It's a window, yeah.
Yeah, but in fact, you can even do better than that. You can figure out what are the best wavelengths by looking at the structure of the extinction coefficients. And people have done this. We did this, but like David Boas, who's coming next week, he's done stuff on that. So it's actually kind of a little surprise. You still want to span that window, but it was a little surprise to me that it wasn't that much of an advantage to be measuring at the isospectic point. Okay.
Thank you.
Yep.
Okay.
Thank you so much for the great lecture, Professor. So a follow-up question to Tim's question. So when you measure optical properties in vivo, have you ever observed, say, like signal fluctuations due to physiological changes?
Due to absorption changes?
Physiological changes, such as like blood flow or changes in oxygen saturations?
Yes, and so tomorrow I'm going to show you tons of those things. So we've observed tons of those things. So today was just a very dry, okay?
So I will ask you tomorrow then.
Yeah,
Thank
yeah,
you.
yeah.
Okay, so we have time for one more question, if anyone wants.
Yeah, question.
Thank you, Professor, for the great talk. In one of the last slides, you talked about fluorescence. And it wasn't very clear to me if you can and how you could find the position of the sources of fluorescence.
Okay, so the problem that I showed you, the homogeneous medium of fluorophores, okay? And the experiment that I showed you was sort of a little sphere of it, in a background where there was nothing. So you could see that there's contrast. But in practice, you have to do the same things that I showed you that we do for absorption. You have to set up an inverse. If you want to be the most general, you have to set up an inverse problem. And I'll show you some data about this tomorrow, but basically you have to figure out what is the distribution of fluence rate in the medium, the excitation. You have to do one tomography problem for that. And then you have to do a tomography problem for using that as a source, generate the fluorescent signal, solve that inverse problem. So it's like double as it's twice as complicated. So the only reason it would be worthwhile to do this is that you can have a much better contrast, and you can. Right? So Gang Zhang will show you lots of really cool ideas he has next week about contrast. I don't know how many of them have made it into human studies, but certainly for animal study, I think it's really very promising. And so that's the key. If you can get a good contrast of tumor to normal, then you can even detect, fluorescence is very sensitive. You could detect very little. If you know that it's not in the background, that's okay, then you can really help yourself.
Okay, thank you.
Okay, so let's thank again Professor Yodh.
Okay.